Hi everyone, my name is Varad Daoo and I welcome you all to this ninth lecture of structure of atom. Right. So my name is Varad Daoo and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. Right. So in the last class, what we have seen? In the last class, we have seen that the drawbacks associated with the Rutherford's model. Right. We saw that the Rutherford's model could not explain the stability of electrons revolving around the nucleus, and also it could not explain the some of the other facts. Right. So for this, a new method, a new model was needed, and this model was given by Bohr's model, right? Then we studied about the numerous postulates of Bohr model, right? And then on the top of that, we studied in detail about those postulates, and then subsequently we studied the advantages of Bohr's model, right? Like what factors which with the Rutherford's model was not able to explain, that were we could successfully explain with the help of Bohr's model. So we studied about that, right? Then we explain we explain the stability of atom, that is the advantage of Bohr's model above Rutherford's model, and we explain the emission spectra of hydrogen atom, right? So in this class, what we are going to study, we are going to study about numerous other aspects of Bohr's model. Like we are going to study the reason behind simultaneous appearance of large number of spectral lines, right, in the spectrum of hydrogen. Further, we are going to study about the Bohr radius or the significance of other energy levels, and we are also going to study about explanation for line spectrum of line hydrogen, and then further at the end we are going to solve some examples, right? So let us start. Right. The first topic, let me write the heading: structure of atom. Right. Lecture 9. The first topic which we are going to study is the explanation for simultaneous appearance of a large number of lines in spectrum of hydrogen. So if you remember, in the previous classes we have studied about various series like Lyman series, Balmer series, right? So we are going to study the explanation for this, right? So this behavior is quite curious, and a question arises as to why hydrogen atom gives so many spectral lines, right? Although it contains only one electron, right? So even though hydrogen has only one electron, there are many lines in emission spectra of hydrogen, right? So this was the question: why, right? So in fact, any simple gas of hydrogen, any sample of gas, so in fact, any sample of hydrogen gas contains a large number of atoms, and when energy is supplied by passing electric discharge, the electrons in the different hydrogen atom absorb different amount of energies, right? Therefore, these are raised to different energy level state, right? For example, the electrons in some atoms may jump to secondary energy level, right? While in others they may be raised to third or fourth or any n energy levels, right? Now the excited electrons come back from these higher energy levels, right? So let me first, in order to understand it, let me first grab a figure. So if you look at this figure, so let us just try to understand it from the example. So let us consider some electrons are present in fourth energy level, right? Some of these electrons will directly jump from fourth energy level to the ground state, right, via route A, right? Whereas others may jump from, let's say for example, if they are coming from fourth energy level to two energy level, and then second energy level, first excited state to the ground energy level, or some of them might come from fourth energy level to third energy level, and then from third to direct ground energy level, or vice versa, right? From fourth to third, third to second, and second to first, right? So some of these electrons will directly jump from ground state, right? Ground state, directly jump to the ground state. Others may jump to second energy level state and then to first energy level state, while others may just drop third, fourth, right? Like this, right? So these four roots are, these are the four roots, right? For this example, we have these four roots, right? So when these excited electrons jump back to various energy level states, they emit different amount of energy, right? And this results into different hydrogen lines depending upon the differences in energy level, right? So let us write this down. So this is one. So we are going to write, right? Any sample of hydrogen, any sample of hydrogen gas contains large number of atoms. When energy is supplied, right? When energy is supplied by passing electric discharge, right? So any sample of hydrogen can contains a large number of atoms, and when energy is supplied by passing electric discharge, the electrons in different hydrogen atoms absorb different amount of radiation, right? Right? Therefore, these are raised different energy states. For example, figure on next page, right? So this figure, what is what we are talking about, right? Right. So when, for example, when electrons jumps from all energy levels other than n equal to 1, right? Right? If electrons are jumping directly from any energy level to this n equal to 1 directly, then the lines which we obtain are called as are in all fall in ultraviolet region, and these lines are called as Lyman series, right? Similarly, the lines obtained when electron jumps to second energy level, right, directly to the second energy level, these fall under visible region, and these are called as Balmer lines. So if I were to tell you using image, so you can see this is the image, right? So if from any energy state the electrons directly go to the ground energy state, then we call it as a Lyman series, right? And these all lie in ultraviolet region. So let's say this is initial state and it directly goes to ground state, or it is at this stage and it directly goes to this stage. Then in such cases we call this a Lyman series, right? And when it goes to n equal to 2, right, then we see it's a Balmer series. Similarly, when it falls from any energy state to directly n equal to 3, we call it as Paschen series. Similarly, when n is equal to 4, it's bracket, and when n is equal to 5, it's found, right? So one thing which you can notice in here is that the energy gaps, right? This is the energy gap, let's say delta E1. This is the energy gap. This is, let's say, delta E2. This is delta A3. Similarly, as we go above, as we go from lower energy to higher energy, the energy gap is decreasing, right? And this is not just for the pictorial representation. It is actually a fact that as we go from energy, lower energy to higher energy, the gaps in the energy level decreases, and that we are going to study further one, right? So the origin, right? So this is by this we have seen. Similarly, the lines obtained when electron jumps to second energy level and equal to 2 from higher energy level is called as Balmer series, right? This is a Balmer series, right? In a similar manner, the transition from higher energy level to n equal to 3 produces Paschen series, right? Similar is the case with bracket and bound series, right? So let us try to do it. So there exists a relationship. So that is what we are going to study. Okay, it's a note. In general, the number of emission lines when an electron jumps from N2 level to N1 level are given by the relation. So this is the expression for that number of lines equal to N2 minus N1 into N2 minus N1 plus 1 divided by 2, right? This is a very important expression, right? Right. So for, let's say, for example, in the Lyman series, when an electron drops from fifth level, that is what N2 is equals to 5 to ground state. Is what N1 equal to 1. Then what we have is number of spectral lines. Would in that case be what? Is 5 minus 1 multiplied by 5 minus 1 plus 1 divided by 2, which corresponds to 20 by 2 by 10, right? And how would these lines be? These lines would be in this following manner, right? So it will, let's say it's at 4. So it will go from 4 to 5 to 4, then 4 to 3, 3 to 2, and 2 to 1, right? So these are all 4 lines. Let's say it's at 4, 4 to 3 it will go, right? Then it can go 4 to 2 or 4 to 1. So these are 3 additional lines, right? And then 3 to 2 it can go, or 3 to 1 it can go. So these are 2 lines. Then 2 to 1 it will go, right? This is 1 line. The total lines 4 plus 3 plus 2 plus 4, which is 4 plus 6, which is 10, right? So let us move on to the last postulate, right, of Bohr's model. No, the advantage of Bohr's model, right? Number third, right? Bohr's theory helped in calculating the energy of electron in a particular orbit of hydrogen atom, right? The Bohr's theory helped in calculating the energy of the electron particular orbit of hydrogen atom, right? On the basis of postulate, right, Bohr derived a mathematical expression for the energy of an electron moving in a particular orbit of hydrogen atom, right? And in this case, he pictured hydrogen atom as a system consisting of a single electron of mass m and a negative charge E evolving in circular orbit, right? So the expression corresponds to En is equals to minus RH 1 by n square, where n equal to 1, 2, 3, right? Where En is what? En is energy of electron, right? This is the energy of electron in nth orbit. Energy of electron in nth orbit. RH is nothing but our constant, right? N is the energy level. Other, right? And this constant, this RH comes out to be 2 pi square me to the power 4 divided by h square, right? Hence, when we couple this together, what we get is En is what? Minus 2 pi square m e to the power 4 by h square into 1 by h square. So remember, these all things are positive, right? These things is all positive, right? That means energy has to be negative, right? It's a negative value, right? We are going to discuss about it. Okay. So substituting the known values, we know what is the value of pi, right? 3.14. We know the mass of electron. We know the charge of electron. We know the Planck's constant, right? So when we substitute the values, what we get is En comes out to be minus 2.18 into 10 raised to power minus 18 by n square joule per atom, right? When we convert it into electron volts, it comes out to be 13.595 by n square electron volt per atom. Why? Because 1 electron volt is what? 1.6022 10 raised to power minus 19 joules, right? And hence when we rearrange it, it comes up to be minus 1138 by n square kilojoule per mole, or we can approximate it as En is equals to minus 1312 n square kilojoule per mole, right? Thus, for each value of n, there exists a possible energy level for the electron, right? So substituting for n is equal to 1, 2, 3, 4, we obtained the E1, E2, E3, and so on and so forth. So these integral numbers n is equal to n1, n2, n3, n4, expressing stationary state of atom, are known as principal quantum numbers, right? So this is a new terminology, right? Just we are giving the name, right? So these integral numbers n equal to 1, 2, 3, so on and so forth, are called as principal quantum number, right? Right, and let us draw the diagram, right? When we put in these values E1, E2, E3, right? When we put n equal to 1, n equal to 2, and n equal to 3, we get E1, E2, E3, right? Let me just plot it. Right, so let's say here we have an orbit, let's say n value, and here we have energy, kilojoule per mole in, right? So let's say this is n equal to 1, n equal to 3, n equal to 3, n equal to 4, and the expression for is minus 13118.8 divided by n square kilojoule per mole, right? So when we put in this n values into this expression, what we get is minus 1311.8, right? Minus 327.9, minus 145.7, minus 8, right? So this is what E1, this is E2, this is E3, and this is finally E4, right? So note which has to be we discussed in the previous class, right? To calculate this value, right? It is clear from above, from the above table, that as the value of n increases, right, the energy difference between successive energy level decreases, right? That means E2 minus E1, right, is greater than E3 minus E2, which is greater than E4 minus E3, and so on, right? Right. So now let us move on to the next topic, right? Energy expected, energy expressions for, right, energy expression for hydrogen like ions. So for the energy expression for hydrogen like ions, it comes out to be En is equals to minus 2 pi square me to the power 4 n square h square, and here instead of for to account hydrogen like ions, we just put in the z square value, right, which comes out to be minus 2.18 10 raised to power minus 18 into z square by n square joule, which comes out to be minus 1311.8 into z by n whole square kilojoule per mole, right? Where Z is the atomic number, right? Right. So now we'll study about the significance of negative, right? We said that energy is negative, right? Significance of negative electronic energy, right? So it is clear from the above relation, right? This relation that En is equals to minus 1388 divided by Z by N whole square kilojoule per mole. So from this expression, it is clear that the energy of an electron is negative in the hydrogen atom, right? So energy is negative because this is positive as it's a square. So there, so these all terms come out to be positive. This is multiplied by minus one, right? So what does this negative energy convey, right? The negative sign of energy means that the energy of electron in the atom is lower than the energy of free electron at rest, right? So what does this mean? So what does negative sign convey, right? So the negative sign, the negative sign of energy means that the energy of the electron is lower than, sorry, the energy of electron in atom is lower than the energy of free electron at rest, right? Energy of free electron at rest, right? So free electron, right? A free electron at rest is an electron that is at sufficiently far away from the nucleus and its energy is assumed to be zero, right? So free electron at rest is an electron that is at sufficiently far away from the nucleus and its energy is assumed to be zero, right? Okay, so this is important. So mathematically it corresponds to the setting. Mathematically it corresponds to setting n equal to infinity in this equation, right? If you put n equal to infinity in this expression, what we get is the energy of free state electron. So as the electron moves closer to the nucleus due to the electrostatic attraction, work is done by the electron itself and hence energy is released, right? Consequently, its energy decreases as it takes energy values less than zero, which means negative values, right? So negative sign also indicates that the electron is bound to the nucleus and a hydrogen atom is in a stable state, is in a stable state in comparison to a state where electron is sufficiently far away from the nucleus, right? So let me write this down. Mathematically, it corresponds to setting n equal to infinity in above equation, right? So as electron moves, closer to the nucleus, right? Closer to the nucleus due to the electrostatic attraction, right? Work is done by the electron itself, and hence energy is released, right? Consequently, right? Consequently, its energy decreases, and it takes energy values less than zero, right? Which means negative values, right? The negative sign also indicates that the electron is bound to the nucleus, and hydrogen atom is in a stable state, right? In comparison to a state where electron is sufficiently far away, sufficiently far away from the nucleus, right? The next topic which we are going to study is the Bohr radius, right? Radius of atom, right? It's called Bohr radius. So Bohr also calculated the radius of first or the ground state of hydrogen atom, and the rest this corresponds to n square h square divided by, so the ground state radius comes out to be around, is represented by r0, and comes out to be around 52.9 nanometers, picometers, sorry, right? Right, and the expression for nth orbit's radius comes out to be n square h square divided by 4 pi square me square z, right? For hydrogen, z is equals to 1, right? So hence Rn is equals to, let us combine this a0 into n square, right? Rn is equals to a0 n square, where a0 is nothing but r0, which is 52.9 picometer, right? Right? So r0 equal to a0 equal to 52.9 picometer is the radius of first stationary state called the Bohr radius, right? Which is 52.9 picometer, and in terms of Armstrong, it corresponds to 0.529 Armstrong. Right? So Armstrong is nothing but 10 raised to power minus 10 meter. Right? Similarly, for n equal to 2, Rn is R2 and R2 is 0.529 into 2 square, which corresponds to, right, or 52.9, 52.9, which corresponds to 2116, 211.6 picometer, right? So on and so forth, right? For hydrogen like atoms, for hydrogen like ions, the expression comes out to be A0 n square by Z, right? Instead of Z square, it comes out to be Z, right? Right? Or in other words, if you want to use the value of A0, it comes out to be Rn is equals to 0.0529 n square by Z, right? Nanometer, right? Then it's very important expressions which we are going, right? The next would be velocity. Velocity of electron in any orbit, right? So velocity expression for that comes out to be velocity is equals to nh by 2 pi mr, right? Where r is nothing but, let's say, Rn Vn. So Rn is nothing but A0 n square by Z, right? Then in that case, Vn comes out to be 2 pi e square Z by n into h, right? So this is important. And then if we substitute all the known values, so we know value of pi, value of e, right? And sorry, and not h we know. And so if we substitute these known values, it comes out to be Vn is nothing but 2.19 into 10 raised to power 6 Z divided by n in meter per second. And if we say the velocity, let's say V0 is the velocity of electron at ground state, then V0 comes out to be how much? V0 comes out to be 2.19 10 raised to power 6 meter per second, and the expression changes to Vn is equals to V0 into Z by n, right? So this is very important expression, right? Then further, if you want to calculate number of revolutions made by an electron around nucleus. So number of revolutions comes out to be V by 2 pi r, and when we substitute the value of r, right, which we calculated, it comes out to be number of revolutions are nothing but 2 pi mv Z square by n square h square, right? So these are all very important expressions which one should remember, right? This is very important, right? Hmm. Right? So now let us try to solve some problems, right? So the question one is the energy difference between the electronic states of hydrogen atom is 214.68 kilojoule per mole. What will be the frequency of light? What will be the frequency of light emitted when the electron drops from the higher to the lower energy state? Right? We know that also Planck's constant has been given to us as 39.79 10 raised to power minus 14 kilojoule second by mole. Right? This has been given to us. So this is a very simple problem. So we know that frequency, that is nothing but mu of emitted light, is related to the energy difference of two energy levels, which is nothing but delta E, as delta E is nothing but h nu, which is nothing but hc by lambda. Right? We are already given delta E value, which is 214.68 kilojoule second per mole, and we are also given h value, which is 39.79 into 10 raised to power minus 14 kilojoule second by mole. Right? Hence mu is nothing but delta E by h, which is 214.68 divided by 39.79 10 raised to power minus 14, which is nothing but 5.39 into 10 raised to power 14 second inverse. Right? Hence mu is nothing but 5.39 10 raised to power 14 second inverse, or 5.39 into 5.39 into 10 raised to power 14 hertz. Right? So this is the answer. Right? Let us move on to the next question. So question number 2. This is important. So according to Bohr's theory, the electronic energy of hydrogen atom in the nth Bohr orbit, right, is given by following expression. En is nothing but minus of 21.76 into 10 raised to power minus 19. Let me rephrase it. Minus 21.76 into 10 raised to power minus 19 by n square joule per atom. Right? Now what we have to do? We have to calculate the longest wavelength of light that will be needed to remove an electron from the third orbit of He plus atom. He plus ion, right? Right. So here for hydrogen-like ions, right? That is He plus ion. We know En is given by 21.76 10 raised to power minus 19 Z square by N square joule per atom, right? Where Z is nothing but atomic number, right? For He plus Z is 2, right? And as we know that it's a third orbit, we know this. We just put it the expression values 10 raised to power minus 19. So here Z is what? 2 by N square. What is N? N is 3, right? Joule per atom, right? Now the energy required to remove an electron from third Bohr orbit of He plus ion is going to be what? Delta E, right? Which is nothing but E3 E alpha minus E3, right? At infinite. So this will be the energy infinite, which is nothing but 0 minus of minus this value, right? 21.76 10 raised to power minus 19 2 by 3 whole square, right? And this energy is certainly going to be hc by lambda, right? This energy is going out to be h nu, which is nothing but hc by lambda, right? Hence we can say h nu, which is nothing but delta I, which is 9.67 into 10 raised to power minus 19 joule, right? Hence this is hc by lambda. Hence lambda is what? hc by 9.67 10 raised to power minus 19, right? So when we put in the values, we get 6.626 10 raised to power minus 34. That is the value of H multiplied by 3 into 10 raised to power 8. That is the volume, that is the value of C. That is the speed of light divided by 9.67 10 raised to power minus 19, right? And hence lambda corresponds to be around 2.055 into 10 raised to power minus 7 meter, or lambda is equals to 205.5 nanometer, right? So this is the answer, right? So in summary, what we have studied today, we have studied the last advantage of Bohr's model, right? Why multiple lines are present in emission spectra of hydrogen atom, right? Further, we have also studied about the Bohr's expression for, or Bohr's radius for nth orbit, also velocity, or velocity expression, right? Velocity expression for electron in nth orbit. Further, we have also solved some problems. So this is where we conclude today's class. So in the next class, what we are going to study about, we are going to study about the dual nature of matter. That means we are going to study about de Broglie wavelength, and then we are also going to study about its origin. Then we are going to study about wave nature of electrons. That is the different experiments like diffraction and inference, the Davis and German's experiment, and then we further study the Bohr's postulate of quantization of angular momentum from de Broglie's wavelength, right? And then in the end, we'll also study about the Heisenberg uncertainty principle, right? So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you.